This turbine is spinning at 3,600 revolutions per minute, producing as much as 600,000 kilowatts of electricity per hour. What powers this turbine? Steam under tremendous pressure. To keep the turbine properly lubricated, pressure is also used to inject oil into the bearings. Gases under pressure are used for welding and burning metals. Pressure created by the elevation of this community water tank enables water to reach homes, schools, hospitals, and businesses. We even ride on tires filled with pressurized air. Pressure is an invisible workhorse, capable of jobs as widely different as powering machinery and cushioning the ride of cars and trucks. But sometimes, pressure can become too great and threaten to damage the system it's a part of. Then, the workhorse becomes a monster. And to prevent damage, we have to have some means of relieving the excess pressure quickly and safely. Excessive pressure in a car's cooling system is released through the radiator cap. In the home, similar devices relieve excess pressure from the kettle, the pressure cooker, and the water heater. On equipment like this high-pressure steam line, pressure relief devices are even more critical. Without them, pressure buildups could damage the system, even rupture it. The cost of such an accident would be considerable, not only in terms of time and money, but also in terms of human injury. In this unit, we'll look at devices that are essential wherever pressure is used. Some of these pressure relief devices are simple. Others are complex, demanding careful attention and precise maintenance know-how. All of them are devices that keep the workhorse from becoming a monster. Before you can deal with the problem of excessive pressure and pressure relief devices, you have to understand what pressure is and how it's measured. What is pressure? Well, first, pressure is force. It can be the force of my hand pressing against the table, or the force of the air in this balloon pushing outward against the walls of the balloon. Most of us know pressure as the force that makes our ears hurt when we swim underwater. But it's not enough to say that pressure is simply a force exerted by one thing on another. Equally important is the area that the force is acting on. Let me show you what I mean. Here we have 6 blocks. Let's say that each block represents 1 pound of force. On this sheet of cardboard, I've drawn 6 squares. Each square measures 1 inch on a side, giving it an area of 1 square inch. So far then, I have force and I have a measured area, but I don't have any pressure. Now I have pressure. I have 1 pound of force pressing against 1 square inch of area. On this 1 square then, I have a pressure of 1 pound per square inch, or 1 psi. If I double the force, now the square is under a pressure of 2 pounds per square inch, or 2 psi. Now, 3 psi. In each case, I'm increasing the amount of force, but not the area that the force is acting on. Stacking all 6 blocks in this way gives me a pressure of 6 psi on the 1 square, and the total force on the cardboard is 6 pounds. Okay, let's see what happens when I arrange the force a little differently. I start with 1 pound per square inch. What do I have now? Well, I've added 1 pound of force, but I've also added 1 square inch of area. So I still have 1 pound on each square inch. When I arrange the blocks so that there's 1 on each square, the pressure remains 1 pound per square inch, or 1 psi, even though the total force on the cardboard is 6 pounds. What this means is that you can talk about force without talking about area. But when you talk about pressure, you have to include force and area. In the English system of measurement, pressure is expressed in pounds per square inch, or psi. But in the metric system, pressure is measured in units called kilopascals. The pressure we'll be talking about are those found in closed systems, like this balloon. As long as the air is sealed inside, the balloon retains its internal pressure. But if we untie the knot, or make a small hole with a pin, the pressure escapes, sometimes violently. So, for the balloon to remain inflated, or a gas bottle or a boiler to remain functioning, the pressure must stay sealed inside. But this raises another question. What happens when the pressure in a closed system rises higher than the system can stand? Well, if the walls of the system are flexible, the increasing pressure will bulge them outward farther and farther. If pressure continues to increase, though, bulging the walls beyond their limit, the system will rupture. And the rupture will occur at the weakest point in the system, the same way that a chain will break at its weakest link. To protect systems from damage caused by excessive pressure, designers and engineers look for a way to relieve excess pressure automatically and safely. The simplest design they came up with was the rupture disc. A rupture disc is a sheet of metal or other material designed to rupture at a predetermined pressure. If this disc is to be used on a system under vacuum, that is, a system whose internal pressure is below atmospheric pressure, then there's nothing to hold it in place or prevent atmospheric pressure from pushing the disc into the system. So, we use a support device to keep the rupture disc bulging outward. The disc and support fit into a holder. Which is bolted in place between two flanges. There are some discs that have a support device built onto them. This system must remain below atmospheric pressure. Whenever pressure rises above atmospheric pressure, the disc ruptures, relieving excess pressure and protecting the system from damage. This is another type of rupture disc called a rebuckling disc. It consists of a disc and a frame with a sharp knife point. A rebuckling disc is installed with the bulge extended into the system and the knife point on the outside. When pressure rises above what is normal for the system, it pushes the bulge outward. When the bulge meets the knife edge, it bursts, relieving the excess pressure. No matter what type of rupture disc is used, the principle is the same. The disc forms a weak spot in the system, saving other parts of the system from pressure damage. And if a rupture disc is placed well away from heavily traveled areas and normal work areas, it also relieves excess pressure safely, away from workers and other equipment. If a rupture disc must be used where workers normally are, it can be connected to discharge piping, which will safely carry the pressurized fluid away when the disc ruptures. Like other devices, rupture discs have both advantages and disadvantages. Among the advantages are that they're simple, lightweight, and very fast opening. In addition, they're relatively inexpensive and require no maintenance except an occasional check to be certain they're not leaking around the edges. They're also manufactured in a wide range of sizes and pressure ratings, from very small discs designed to rupture at pressures as high as 200,000 psi to very large discs, such as the one on this turbine exhaust hood, designed to rupture at only a few psi. As a general rule, the larger the disc, the lower its pressure rating. The biggest disadvantage of rupture discs is that when one ruptures, it has to be replaced. And to replace it, the system must be shut down. Downtime is costly. So, rupture discs are usually limited to use on systems where problems with excessive pressure are very unlikely. When you do replace a rupture disc, there are certain things to be very careful of. Make sure, for example, that the replacement disc has the same pressure rating as the original. Replace a 205 psi disc with a 590 psi disc, and the new disc won't rupture until long after excessive pressure has damaged the system. Replace a 205 psi disc with one rated at 100 psi, and you'll have the opposite problem. The disc will burst at normal system pressure. If the original disc required a support device, be certain to install a support device with the replacement. Because if you don't, and you forget the support, the disc is likely to collapse inward and rupture long before it's supposed to. To avoid common installation mistakes, always consult the manufacturer's instruction manual before beginning. Knowing what to do before trying to do it saves everybody time, effort, and money. We've learned what pressure is and what it can do when it gets out of hand. We've looked at the most simple type of pressure relief device, the rupture disc. We've seen that although a rupture disc is effective, fairly inexpensive, and requires only minimal maintenance, it has one major drawback. When a disc does burst, the system usually has to be shut down to replace it. This disadvantage of rupture discs sent designers back to their drawing boards to find more versatile pressure relief devices. We'll see one of the devices they came up with in the next segment. It's a basic fact that the more complicated the job you want a device to do, the more complicated the device usually has to be. Pressure relief devices are no exception. Rupture discs can be simple because all they're designed to do is relieve excess pressure. But if you want a device that not only opens to relieve pressure, but also closes when system pressure drops back to normal, you're talking about a more complicated device. If you want that device to be adjustable as well, that too adds complications to the design. This pressure relief device meets both requirements. It closes after relieving excess pressure, and it can be adjusted as necessary to maintain a very accurate set point. It's called a relief valve, and it's used primarily on systems that handle pressurized liquids. To understand how a typical relief valve works, let's start with its basic parts. The outer shell is called the valve body or valve casing. It gives overpressurized liquids a path to flow through, as well as holding the internal parts of the valve in their proper position. A look inside the valve body shows the inlet and the outlet. On this particular valve, the inlet and outlet are both threaded. The threads enable the inlet to be connected to the system, and the outlet to be connected to discharge piping. In many high-pressure applications, though, the inlet might be flanged or even welded directly to the system the valve is protecting. When system pressure is normal, the path from the inlet to the outlet is blocked by the disc, also called the plug. Liquid is prevented from leaking around the disc by firm, even contact between the disc and a seat. In some valves, the seat is a permanent part of the valve body. In others, a threaded seat bushing is used. Because it's threaded, a seat bushing can be replaced if necessary. Guiding the up and down motion of the disc is the spindle or stem. Often, it too is threaded so it can be screwed directly into the disc. To hold the disc in place against normal system pressure, a spring is used. A spring washer forms a flat surface on top of the spring to ensure even contact between the spring and the adjusting screw. The adjusting screw fits down over the end of the spindle and screws into the valve body. This screw exerts downward force on the washer and spring and can be used to adjust the tension of the spring. A lock nut holds the adjusting screw in position once it's been set, and a cap covers the top of the assembly, protecting the internal parts from dirt and damage. That gives us the basic parts of a relief valve. Now, let's see how a relief valve works. Let's assume that normal system pressure for the system this valve is protecting is 18 psi, and that the valve is set to open at a pressure of 20 psi. When system pressure reaches 19 psi, nothing happens. Pressure is still at a safe level. At 20 psi, though, the system pressure pushing upward on the disc begins to overcome the tension in the spring. The disc begins to lift off its seat, releasing pressurized liquid through the outlet. At 21 psi, the pressure lifts the disc even higher, and as pressure increases, the disc continues to lift until it has risen as far as it will go. This particular valve reaches its fully open position when system pressure reaches 25 psi. The difference between the pressure at which the valve begins to lift 20 psi and the pressure at which the valve is fully open, 25 psi, is called the accumulation of the valve. We say then that this relief valve has an accumulation of 5 psi. Another term you should know is lift or travel. Lift or travel is the distance the disc moves from its closed to its fully open position. In this valve, the lift is about 1 inch. In other relief valves, lift ranges from fractions of an inch to several inches. The valve has done its job. It's relieved excess system pressure. Now, let's watch what happens as system pressure returns to normal. As pressure decreases, the upward force on the disc decreases. Thus, the tension in the spring gradually gains the advantage again and moves the disc back down toward its seat. At 20 psi, the pressure at which the valve began to lift, spring tension and system pressure are equal. The disc is reseated. When pressure drops further, spring tension completely overcomes system pressure, firmly holding the valve closed. You can see how important proper spring tension is to the function of a relief valve. But, like any other component, springs wear after extended service, losing some of their stiffness. This changes the opening and closing point of the valve. To correct this, the spring adjusting screw can be tightened. This increases tension on the disc and raises the opening pressure of the valve. Loosening the adjusting screw has the opposite effect. It reduces the amount of tension on the disc, allowing the valve to open at a lower pressure. Remember, though, that each relief valve is designed to handle a certain range of pressures, so each can only be adjusted so much. So, before making any adjustment to any relief valve, consult the manufacturer's instruction manual. Know exactly what you're doing before you do it. I mentioned earlier that relief valves are used primarily on systems that handle pressurized liquids like cooling water, lube oil, and fuel oil. For gas and vapor systems, you'd normally use another type of pressure relief device, a safety valve. We'll see what a safety valve is and how it works in the next segment. At the end of the last segment, we looked at the basic parts and functions of relief valves. We also said that relief valves are used primarily on systems that handle liquids, like water or oil. But that leaves us with an unanswered question. Why not use a relief valve on a steam or gas system? The answer lies in the differences between liquids and gases. There are two major differences. First, gases take up a lot more space than liquids do. As a matter of fact, if I boil 1 cubic inch of water, the steam generated will fill a space of over 1,500 cubic inches. What does this mean in terms of relieving pressure? Well, if in a water system you have to let 1 cubic foot of water escape to relieve 1 psi, in an equivalent steam system you'd have to allow over 1,500 cubic feet of steam to escape to lower the pressure 1 psi. That's quite a difference. The second major difference between liquids and gases is that liquids cannot be compressed, while gases can be compressed. We can demonstrate the difference between liquid and gas with this graphic of a closed system. The system consists of a tank that holds the liquid or gas, a piston for exerting pressure on the fluid, a pressure gauge to tell us the pressure in the system, a relief device designed to open at 5 psi and close at 0 psi, and a spill tank for collecting whatever fluid the relief device releases from the tank. Let's start by filling the tank with water. With the piston fully retracted, the gauge tells us that the system pressure is 0 psi. But watch what happens when the piston begins to press against the water. As soon as the piston moves, system pressure increases. As a matter of fact, system pressure increases in direct proportion to the movement of the piston. At 5 psi, the relief device begins to open and water flows into the spill tank. Immediately, system pressure drops. Here we can notice something very important. Because water, like any other liquid, is not compressible, the amount of water discharged into the spill tank must equal the amount of water displaced by the piston. As the piston displaces a greater volume of water, the same volume of water must be released into the spill tank if system pressure is to be maintained at a safe level. Now, let's see what happens when the system is filled with a gas, like air. Again, we start with the piston fully retracted and the gauge reading 0. The relief device is, of course, closed. The piston begins to move forward, but notice that there is very little change in the system pressure. As the piston continues moving, system pressure increases, but not nearly at the rate it did when the system was full of water. The piston must move a considerable distance to compress the air enough to raise system pressure to the opening pressure of the relief device. When the relief device does open, the air shoots through the opening at a high velocity, quickly expanding back to its original volume in the spill tank. Because the piston has had to compress such a large volume of the air before the relief device opened, however, it takes a relatively long time for enough air to be released into the tank to return the system to original pressure. Because of the way gases and steam act, putting a relief valve on a gas or steam system leads to two major problems. First, a relief valve opens gradually. It doesn't open quickly enough to let out the tremendous buildup of gas or steam causing the excess pressure. By the time a relief valve opens all the way, pressure would be far beyond the safety limit. Secondly, when a relief valve first begins to lift and the disc and seat are just a small space apart, the velocity and the temperature of the escaping fluid would actually cut the metal. When a disc is damaged like this, we say that it's steam cut or wire drawn. To relieve a lot of steam or gas very quickly, while at the same time preventing damage to the metal parts of the valve, we need a device that pops wide open instead of lifting gradually. The device we need is a safety valve. This is a huddling chamber safety valve. Like the relief valve we saw earlier, a safety valve consists of a valve body, or casing, which forms an inlet and an outlet for system pressure to flow through. It also has a disc, sometimes called a feather, and a seat, which in this case is a replaceable seat bushing. The disc is held against its seat by a spring. The lift of the disc is guided by a disc guide and a spindle, which is attached to the disc and runs through the center of the spring. Unlike the relief valve we saw, this safety valve has two spring washers, one above and one below the spring. These hold the spring in place. A spring adjusting screw controls spring tension, and a lock nut holds the adjusting screw in proper position. So far, this safety valve is almost identical to a relief valve, but a safety valve has some parts that a relief valve may or may not have. First, there's a release nut at the top of the spindle. The release nut is part of a hand lifting assembly, which includes one or two lifting levers. Each lever is connected to the valve with a pivot pin. For testing the valve and for making certain it is clear of any obstructions, the levers are raised. The levers, in turn, push upward on the release nut, lifting the spindle and disc. The valve closes again when the levers are lowered. The hand lifting assembly and top of the spindle are covered by a valve cap. A big difference between a safety valve and a relief valve is the shape of the disc. Notice that the disc or feather of a safety valve has a lip which is not exposed to system pressure when the valve is closed. Notice also that there is a small chamber called a huddling chamber just below the disc, and an adjusting ring that's threaded onto the outer edge of the seating area. The adjusting ring is prevented from turning by a ring pin that protrudes through the wall of the valve body. Now, let's see how these components work together. The pressurized fluid, usually gas or steam, is always in contact with the center portion of the disc, called the pressure sensing area. Again, let's assume that normal system pressure is 18 psi and that the valve is set to open at 20 psi. At 19 psi, nothing happens, but at 20, the disc or feather begins to lift off the seat. Suddenly, the lip of the disc, which wasn't exposed to system pressure, is exposed to system pressure. Because a larger area of the disc is exposed, there is more total force being exerted on the disc, even though system pressure remains the same. The increased force causes the disc to pop open to about 60%. Two forces hold the disc in this 60% open position: system pressure and the velocity of the escaping steam striking the disc. If system pressure increases further, the velocity of the steam also increases, and the two forces will lift the disc even higher. What does the initial popping of a safety valve accomplish? It instantly gives overpressurized gas or steam a wide escape route. The wider the escape route, the less velocity the escaping fluid has. By reducing velocity, the popping action of the valve minimizes the steam cutting that can result from a high velocity flow of steam. So, now we know that there's a major difference between the way a relief valve opens and the way a safety valve opens. What about a difference in the way they close? Again, here's our safety valve, still in its fully open position. System pressure begins to decrease, and along with it, the velocity of the steam. Spring tension begins to regain the advantage, pushing the disc downward. Now system pressure is at the point where the valve first opened, but because the lip of the disc is still exposed to system pressure and steam velocity, the valve remains open. Only when system pressure drops below the set point of the valve does the valve snap shut. The valve snaps shut instead of closing gradually to abruptly cut off the flow of steam, thereby minimizing steam cutting. A small cushion of steam trapped in the huddling chamber prevents the disc and seat from slamming together hard enough to be damaged. Now that we've seen the basics of how a safety valve operates, let's go back and watch the operation in greater detail. As we do, we're going to learn a few new terms: popping pressure, simmering, blowdown or blowback, positive seating, and chattering. We're also going to explore the purpose of the adjusting ring that we mentioned but never explained. Once again, here's our safety valve. System pressure is normal now, and the valve is adjusted to open at 20 psi. 20 psi then is said to be the popping pressure of the valve, the pressure at which the valve will pop open. System pressure increases. When it reaches popping pressure, the disc rises off its seat, but it hasn't popped yet because the pressure hasn't had time to act on the lips of the disc. This condition, where the disc has lifted only slightly, is called simmering. Usually, simmering lasts only a split second until system pressure acts on the lips of the disc, and the valve pops open. System pressure continues to rise, then levels off, and begins to drop. Even when pressure drops back down to popping pressure, the valve remains open because the lip of the disc is still exposed to system pressure and steam velocity. Only when system pressure has dropped below popping pressure is the spring able to shut the valve. When the disc is firmly in place against its seat, we say that the valve has positive seating. Positive seating is important to ensure that there is no leakage. The difference between the popping pressure and the positive seating pressure is called the blowdown or blowback of the valve. In our example, the popping pressure is 20 psi. Positive seating occurs at 19 psi. So the blowdown of the valve is 1 psi. Why is blowdown important in a safety valve? Well, let's consider a case where the popping pressure is 20 psi and the positive seating pressure is also 20 psi. When pressure reaches 20 psi, the valve simmers and lifts and continues to rise as pressure increases. When pressure drops back to 20 psi, the disc returns to its seat. But because 20 psi is both seating pressure and popping pressure, as long as system pressure remains at 20 psi, the valve can't make up its mind whether to remain closed or pop open again. In this situation, the disc is likely to jump up and down on its seat until pressure either increases enough to pop it or drops enough to give it positive seating. This up and down action is called chattering or machine gunning because of the sound it makes. Chattering is a serious problem. It can severely damage the disc and the seat. Blowdown prevents chattering by ensuring that popping pressure and positive seating pressure are different. Just as the popping pressure of a safety valve can be adjusted by turning the adjusting screw and increasing or decreasing spring tension, blowdown is adjusted by changing the setting of the adjusting ring. We can see how the position of the adjusting ring affects blowdown by studying what happens when the valve is closing. Remember that the position of the disc is determined by both the amount of system pressure and the velocity of the steam striking the disc. The adjusting ring acts like the nozzle of a garden hose. In a raised position, it directs the escaping steam right against the disc. Because most of the steam is aimed at the disc, the velocity of the steam exerts a large amount of upward force. Because of this added force, system pressure must drop well below popping pressure before the spring can force the disc back onto its seat. Raising the adjusting ring, then, increases the blowdown of the valve. Starting once again with the valve in its open position, let's lower the adjusting ring and see what happens. Without the ring directing steam at the disc, much less escaping steam strikes the disc on its way to the outlet. As a result, the velocity of the steam exerts less upward force on the disc. Because the system pressure is getting little help from the escaping steam, it takes more system pressure than before to hold the disc open. With the adjusting ring in this position, the valve will close against higher system pressure than when the ring was raised. As a result, the blowdown of the valve, the difference between popping pressure and positive seating pressure, decreases. As a general rule, then, the higher the position of the ring, the higher the blowdown. The lower the position of the ring, the lower the blowdown. To get a better understanding of one-ring huddling chamber safety valves, read through Section 3 of your text and answer the questions there. Then, in the next segment, we'll look at other types of safety valves and how they function. In the last segment, we learned that the major differences between relief valves and safety valves are not only differences in design, but also differences in function. Where relief valves open gradually and are best suited for liquid systems, safety valves pop open and are best suited for quickly relieving high volumes of gases with minimum danger of steam cutting. Safety valves also have a characteristic called blowdown, a difference between popping pressure and positive seating pressure. Popping action and blowdown are characteristics of all safety valves, including the three types we will look at in this segment: the two-ring huddling chamber safety valve, the three-ring huddling chamber safety valve, and the nozzle reaction safety valve. As its name suggests, a two-ring huddling chamber safety valve has both an upper and a lower adjusting ring. The upper ring has two jobs: to adjust the size of the huddling chamber outlet and therefore the blowdown of the valve, and to direct the steam downward away from the disc. As we'll see in a moment, changing the direction of the flow in this way increases the amount of total force exerted on the disc. Raising the upper ring gives escaping steam a wide, straight path to the outlet. Because little of the escaping steam acts on the disc, the valve can close at a higher system pressure. This means a smaller blowdown. Raising the ring too much allows so much of the steam to escape without acting on the disc that the valve may not be able to lift all the way. Lowering the ring, on the other hand, narrows the escape route, making more of the steam act on the disc. It also directs steam downward, which creates a force called a reactive force. It's easy to demonstrate what a reactive force is. This balloon is full of air. If I let go of its open end, the air will rush out in this direction, but the balloon goes in the other direction. Why? Well, the force of the air rushing outward in one direction creates an equal force going in the opposite direction. This equal but opposite force is what we call a reactive force. In exactly the same way, pressurized gas or steam directed downward by the upper ring will exert an upward force on the disc. So, in its lower position, the upper ring not only narrows the escape route of the steam, but also helps to create a reactive force. The end result is a greater blowdown of the valve. The lower ring also has two jobs. It directs escaping steam directly at the disc, ensuring a clean, forceful popping action. And it traps a cushion of steam that softens metal-to-metal contact when the valve closes. If the lower ring is set too high, the space between the ring and the disc becomes too narrow. Because steam cannot escape as quickly through this narrow space, the blowdown of the valve is increased. Setting the lower ring too low allows the steam to escape without hitting the disc. The valve could simmer too long before popping, or it may not pop open at all. In addition, if the lower ring is set too low, no cushion of steam is formed to soften contact when the valve snaps shut. You can see then that proper positioning of the adjusting rings is extremely important. It should be done only by an experienced mechanic who has consulted the manufacturer's instruction manual and knows precisely how the rings should be set. And once properly set, the ring should be locked in place by tightening the ring pins that protrude through the valve body. That covers a two-ring huddling chamber safety valve. Now, how about this one, the three-ring type? A three-ring huddling chamber safety valve is basically a two-ring type with a third adjusting ring situated between the other two. This ring is adjusted to either cover or expose a series of radial holes drilled in the upper ring. When fully exposed, the radial holes allow steam to escape, which reduces the amount of steam hitting the disc. If the holes are completely exposed, not enough steam will reach the disc to open the valve all the way. Also, blowdown will be very small. On the other hand, if the middle ring completely covers the holes, so much steam hits the disc that the valve will open with too much force, which could easily damage the disc. And of course, blowdown will be rather large. To ensure that the middle ring is positioned properly, all adjustments are made at the factory. This prevents the need for adjustment during normal maintenance. The third type of safety valve we want to look at is this one, the nozzle reaction safety valve. The nozzle reaction safety valve gets its name from the nozzle shape of its inlet and the way it uses reactive force. Most nozzle reaction safety valves have two adjusting rings. The upper ring is called the guide ring, and the lower ring is called the nozzle ring. The guide ring and nozzle ring work together in a unique way. As system pressure rises to the simmering point, the disc rises off its seat. Due to the shape of the disc, the path of the steam is turned downward, creating a reactive force. The steam then strikes the top surface of the nozzle ring and is directed back toward the disc. Again, the steam changes direction, creating a second reactive force against the disc. Together, these separate forces cause the disc to pop open. When the disc pops, it exposes the inner surface of the guide ring. Steam deflected off the guide ring adds yet another reactive force against the disc, lifting the disc still higher. Adjustment of the rings is the same for nozzle reaction valves as for two-ring huddling chamber valves. Raising the guide ring widens the escape path for the steam, decreasing the blowdown. Lowering the guide ring narrows the escape path, increasing lifting force and blowdown. Raising the lower ring directs more steam against the disc, which can lead to prolonged simmering if the ring is adjusted too high. Lowering the lower ring decreases the amount of steam directed against the disc. Adjusting it too low eliminates the cushion of steam necessary to prevent damage when the valve closes. If you're beginning to get the idea that there are a lot of different types of safety valves, you're right. Although we've seen the most common categories, we can't hope to cover all the types you're likely to run across. Just remember, if it's a safety valve, it's going to pop open and it's going to have blowdown. Keeping that in mind and reading through the manufacturer's instruction manual for specific information on whatever safety valve you're working on will give you a head start on understanding and maintaining almost any safety valve made. Some of the pressure relief devices you'll come across, though, are outside the category of relief valve or safety valve. Nonetheless, they're important devices that you should be familiar with. In the next segment, then, we'll look at two such devices. The list of different pressure relief devices available today doesn't end with rupture discs, relief valves, and safety valves. There are other devices which, because of their versatility or some other characteristics, have found their way into common usage. Two such devices are the safety relief valve and the pilot actuated or PA relief valves. As its name tells us, the safety relief valve can be either a safety or a relief valve. In some cases, the valve will automatically work as a safety valve on an air system and a relief valve on a liquid system. But for use on a steam system, the entire insides of the valve have to be replaced. In other cases, the safety relief valve is a safety valve when the adjusting rings are positioned one way and a relief valve when the rings are positioned another way. The safety relief valve shown here is a good example of the second type. It's very similar in construction to a nozzle reaction safety valve, with a nozzle-shaped inlet and both an upper and a lower adjusting ring. The way it's set up here, this valve is ready for service as a safety valve. The lower ring is adjusted upward to direct fluid against the disc, causing the valve to pop open. In this position, the lower ring also traps a cushion of gas or steam to soften impact when the disc closes again. To use it as a relief valve on a liquid system, all that has to be done to this particular valve is to lower the bottom adjusting ring. With the bottom adjusting ring in this position, fluid is not directed at the disc. As a result, the disc will rise gradually instead of popping open. What's important for you to know is that whatever changes or adjustments are required are done by the valve manufacturer before you receive and install the valve. Converting safety relief valves from one type to the other is not a part of your job. Okay, now let's go on to the second pressure relief device we're going to look at in this segment, the pilot actuated or PA relief valve. This type of pressure relief device is known by any of several names: power-actuated pressure relief valve, electromatic relief valve, pressure-matic relief valve, but they all mean about the same thing. Regardless of what you call it, a PA relief valve consists of two major components: the valve itself, which is similar in shape to other valves we've seen, and a separate pilot device that senses changes in system pressure and tells the valve when to open. Let's start with a close look at the valve. The first thing to notice is that the spring is below the disc, and that the disc opens downward, allowing steam to escape through the upper part of the valve body. The PA valve also has a disc guide that aligns the disc with the seat. A small opening between the guide and the disc allows system fluid to pass through it from the inlet to the bottom of the main disc. Because of this feature, during normal system operation, system pressure is exerted on both top and bottom of the valve disc. If system pressure increases, it increases on both sides of the disc. Because the pressure on the bottom counterbalances the pressure on top, the valve will not open. That brings us to the pilot device. The pilot device consists of a pressure sensing tube, an electrical relay, a solenoid, and a pilot valve. Like the other pressure relieving devices we've seen, the pilot device is set to open at a predetermined pressure. When system pressure reaches that point, it is also acting on the pressure sensing tube. The tube activates the relay, which in turn closes the electrical circuit, energizing the solenoid. The solenoid then lifts the pilot valve, and excess pressure is vented. Where is this pressure coming from? It's coming from below the disc of the main valve. When the pilot valve bleeds off this pressure, the only pressure remaining is the pressure above the disc. Without pressure below the disc countering it, the pressure above the disc easily overcomes spring tension, and the valve opens, relieving system fluid through the outlet above the disc. When system pressure returns to normal, the pilot valve closes, and pressure builds up once again below the main valve disc, helping the spring to hold the disc closed. PA relief valves are used on gas and steam systems, so, like safety valves, they pop open and have a predetermined amount of blowdown to prevent chattering. Where will you find PA relief valves used? You'll usually find them on the same systems that use safety valves. As a matter of fact, safety valves and PA relief valves are often used together. In such cases, the PA relief valve is set to open at a lower system pressure than the safety valve or valves. In this way, the PA valve goes off first. The reason for this is simple. By law, safety valves cannot be isolated from the system they're protecting. Therefore, if a safety valve suffers steam cutting or other damage, the system must be shut down to make repairs. PA valves, on the other hand, can be isolated from the system because they are not figured into the design of system safeguards. They're an extra measure. Since they can be isolated from the system, PA valves can be used and then repaired if necessary without having to shut down the system. As a result, having them online with safety valves saves wear and tear on the safety valves and prevents costly shutdowns. In this unit, we've seen quite a variety of pressure relief devices, from simple rupture discs to the more complicated safety and PA valves. Aside from differences in their design and operation, all the devices we've seen perform the same function. They relieve excess pressure before it damages the system. Because of their great importance, it's essential that you understand how each device works, that you familiarize yourself with the specifics of the valves you'll be working on, and that you learn the safest and most efficient way to keep these devices in top working condition. With safety and relief valves, perhaps more than with any other type of equipment, maintenance mistakes can be costly and dangerous. Don't take chances. Consult the manufacturer's instruction manual before starting any valve maintenance job. Know exactly what to do before you try to do it.